Okay, so let me welcome Ido to give our first seminar for the semester in our math phys CHEP seminar. And he's speaking from Berkeley. It's late at night, but hopefully, it will be okay. So the title of the talk is Grand Canonical Multiverse and the Cosmological Constant. So please take it away, Ido.
Okay, so thanks a lot for having me here, and yeah, it's a great honor to actually to open the year with this talk. So yeah, so I'll discuss my work with my collaborators Meirav Haddad and Amir Michaelis about the grand canonical multiverse and the cosmological constant. Of course, from the title you can understand that it's a rather speculative talk, and the idea is mostly yeah, so it's with ideas which I think are interesting, and I hope that people will pursue them further, including, of course, myself. So the outline of my talk will be, I'll discuss a bit about inflation and internal inflation and problems with these notions, and then I will briefly explain the cosmological constant problem. And then I will go on to our work, which is thinking about, or maybe some model of the multiverse, or thinking about the multiverse as a thermodynamical system, and what are the implications of such a thinking on the cosmological constant. And I'll end with discussion. With the discussion is, of course, will be open questions and ideas that are worth thinking about. So inflation, as I guess many of you know, so that's a period of accelerated expansion at the very early universe for at least 50 or 60 e-folds. And during inflation, the Hubble parameter is roughly constant, which results in this exponential expansion of the scale factor. Historically, it was suggested as a solution to the horizon and flatness problem. More interesting is that it has very definite predictions for the cosmic microwave background radiation, which have largely been verified. There are, of course, many realizations of inflation. The simplest and most common one, and actually which also is a very good fit to the data, is a single canonical scalar field. So if we assume that we have a scalar field with a potential, for instance, this is a plot of a potential, which is a valid model of inflation. So, right, we want to be in the slow roll regime, which means that the slow roll parameters, which depend on the potential and its derivatives, we want them to be much smaller than 1. And if that's the case, then we can evaluate the spectral, the power spectrum, the scalar power spectrum, which describes the density fluctuations, and the tensor power spectrum, which describes gravitational waves. We can calculate them using these slow roll parameters and try to match that to observations. And this way we can confirm or rule out models. So, so far, observations have measured the amplitude of the scalar power spectrum, the tilt, the power law here, to a very good accuracy of about 1%. However, regarding the tensor spectrum, the gravitational waves, we only have an upper bound, which is consistently getting better and better. And yeah, this is, of course, this cartoon that, okay, the universe is like a ball that is slowly rolling down the potential and then reaches the minimum. So here, of course, it doesn't stop, but you have a reheating, which is because the field oscillates here around the minimum. And this is where reheating takes place, and the universe is populated with the known particles of the standard model. So this is an update of the observational versus the theoretical status. So what we have here, we see this plot of the NSR plane. So NS is the N sub S is the spectral tilt or spectral index of the density fluctuations. And R is the tensor to scalar ratio, a probe of gravitational waves. And since this is so easy, all you need is some potential with a few parameters. Then there is a fascinating zoology of models, many models. You want to try to divide them into subclasses and subclasses. And what we can say today is that the most simple models, the poster child models that we had for 20 years, which are the monomial models, are ruled out by current data. So this is the most up-to-date data, including BICEP3 data. And we see that NS is a constraint to roughly 1%, to be around 0.9, between 0.96 and 0.97. And R is currently bounded to be less than 0.036. So, okay, so even if we take this power here of the field to 0, it's still ruled out. And this is important. So this is important to remember. So this is the success of inflation, the very good fit of single scalar field inflation to the CMB. What are the questions that we have about inflation? Sorry.
Sorry,
what are
can you just flash the previous slide a second? I just wanted to look at the models which you said were ruled out.
Yes. Sorry. Yes.
So I guess the bottom part is oh, I see. So the point is that the higher power, the low, it has to be a lower power model. Is that the statement? It has to be a constant. Is that to be a constant in some? What is the right?
Yes.
What is this? I see.
So if you want a monomial model, which originally it was m squared phi squared, phi to the fourth, etc., and then axial monodromy is this phi to the 2/3. So of course you can take even if you take log phi, this is not not a good fit to the data anymore. So you cannot have a monomial model anymore. It has to be at least.
So I'm trying to put that in the context of the statement that you made before, which is that even this, there are this. What you're saying is that the single field models can work, but within single field models, there are simple polynomials and powers like that are ruled out. That's the statement.
Exactly. So if so if you have not a monomial but a polynomial, if you have a constant plus phi squared plus etc., then of course this model work very well, right?
Yeah.
And
I confused myself. I confused myself.
Of course, many single field models work very well. I just wanted to state that the simplest one, which are the most predictive ones, these monomial models don't work anymore. Okay, that's all. Okay, so what are the few open questions about inflation? So this is, of course, a matter of taste, but to me, the most interesting thing is that inflation does not resolve the Big Bang singularity. So even if inflation, so we will have at some point need to answer what are we doing with the Big Bang singularity, maybe with quantum gravity, maybe by having a bounce or whatever. So it's important to remember that inflation does not resolve that. And therefore, it's interesting, and one should keep an open mind of whether, once we do solve the singularity problem, what does it mean for inflation? Other issues, which are, so this is my personal opinion and my favorite problem of inflation, let's put it this way. Now, other issues which have various levels of seriousness. So there's the initial condition problem, which is, if the evolution is unitary, right? So the phase space volume is conserved, and therefore, the fact that we're saying we have inflation, it's not like we had a larger, it's not like we had a more generic phase space of initial points in the phase space that converge to inflation. It's simply exactly the number of phase space points that give you inflation are exactly, they're the same part of the phase space, regardless if it was before or after inflation. That's one question, usually, I think, originally raised by Roger Penrose. Another is, okay, so if we start from some more arbitrary metric, which doesn't have a lot of symmetry like FRW, do we converge to inflation? And actually, a very interesting work which strengthens the case for inflation has been done by these two people, Matt Kleben and Leonardo Senatore in 2016. So that's a good, there is some advance in this direction. And then, as I said, simplest models are ruled out. And finally, quantum gravity. So from what we know of quantum gravity today, from the past 20 plus years, it seems that definitely in string theory, it's very difficult to construct explicitly and directly metastable de Sitter solutions or inflationary solutions. And it seems that maybe this is something more general about quantum gravity, even if we don't specifically discuss string theory. And this has led to this swampland conjectures. So I don't know if this square is hiding some of these conjectures, but one of them is that the field trajectory should be less than Planck, than M Planck, because beyond that, then you should expect to see more and more light states, which invalidate your effective field theory. And then another more recent one called the Swampland conjecture is the fact that on top of this distance limitation, this derivative of the potential divided by the potential, first or second derivative, one of them should be order 1, which is not what we want if we want slow roll inflation, right? For slow roll inflation, we want both of these to be much less than 1 at CMB scales. So these are various problems, and then and then we reach what is called eternal inflation. So what is eternal inflation? So what I've described so far as inflation or slow roll inflation is in this region. So this is of course the m squared phi squared potential, but this is valid for other potentials as well. And the idea is the following: in this regime, you have the classical slow roll evolution, and on top of that you have small quantum fluctuations. These are the quantum fluctuations that we observe on the CMB sky, and they are small, and therefore the classical evolution is a good description. And this is where we get the density power spectrum, which is roughly 10 to the minus 9. So for all observational purposes, the picture is working very well. Okay. The thing is, okay, what if we trust our potential, this m squared phi squared, the Starobinsky model, or the whatever model that you like, a small field model, whatever. What if we trust it to much larger values? So assuming if we can extrapolate this potential to much larger values, so the derivative of the potential is still small, but the value of the potential is much larger. And when this quantity, the power spectrum, reaches 1, we reach a situation where the quantum fluctuations are so large, they dominate over the classical evolution. Okay, so in that case, what happens is that although parts of the universe go through the classical slow roll evolution, other parts will fluctuate upwards and will have a higher cosmological constant and will inflate in a more rapid way. And this method will happen in these universes again and again and again and again. Okay, indefinitely. So this is what is leading to the so-called multiverse. Here, and actually I have this is from Andre Linde's website, so I will just flash it. This picture. So here you can see, here is a numerical that you start with some small initial fluctuations and how actually the fluctuations go larger and become larger and larger and dominate. So you see all these fractal surfaces are, regions where the inflationary potential or the cosmological constant is larger, and therefore they will expand more rapidly and dominate the volume of the multiverse. Okay. So it is, one reservation that one can make is that obviously this is an extrapolation of the potential from CMB scales to much higher scales. So obviously it can be modeled around. One may say that, in string theory, if we expect exponential potentials, so the potential will always be very steep, except in some small region where we'll arrange for such a small region where we have slow roll, and therefore in such a case, eternal inflation never happens, and okay, no, you don't have a multiverse. But it's fair to say that the community, most of the community, does take this seriously and thinks that, yeah, we do have this problem, maybe feature, whatever, advantage of the model, that we have this eternal inflation, and therefore we have a multiverse and not just a universe. So, and here this is an artist impression taken from a Scientific American article that Andre Linde wrote. So you see here I have a universe. It creates more new universes, more and more universes. Now each color could represent different physical laws, different cosmological constants, etc., etc. And this process repeats itself. And obviously, if you do the calculation. So the vast majority of universes are still inflating. And actually, you know, the largest cosmological constant should dominate the volume of the universe. So you should expect to be, naively, you would expect to be in a universe which is now inflating with in the largest possible speed. So questions so far before I continue.
So I'll just ask something. Maybe like it's kind of well known, but so if I would think that these large values of the potential that you need for this sort of thing would happen also at large field values, right? So I mean, so would these same regions be in the same effective field theory because of the swampland, you know, field range bound and all that sort of thing?
Right. So that's also my reservation that, you know, okay, from what we know, even from very basic field theory, obviously you have corrections, right? And therefore, if these corrections, I mean, so, you know, this has to be decided model by model, but naively this, you know, if these corrections are relevant, then you will never reach this eternal inflation regime. Yeah, I agree with that. And definitely the swampland means that, you know, the distance conjecture means that you'll have a tower of light states that you'll have to take, you know, take into account.
Yeah, and so the effective field theory will have to have some sort of other description or something like that. So that, so
right,
yeah,
right,
yeah.
So yes, so let's say for the that we do think that, okay, eternal inflation may have occurred. What does it mean for inflation as a theory of nature? So it immediately gives it immediately causes a very serious problem with predictability, because if you follow the logic, and you know this it's cited in papers, it's not just some coffee discussion, anything that can happen will happen infinite number of times. So this I always like to say. So if eternal inflation happened, there is a universe where a guy named Andre Linde says that the multiverse is garbage, and the guy named Paul Steinhardt that says that, of course, the multiverse is correct. So so then, you know, how can we predict things? How can we, you know, if any prediction like the scalar spectrum is just happening in our universe, and in other universe you have different power spectra, you have different physical laws, in what sense is the theory predictive? Okay, and if we want to try to make predictions and make sense of our predictions, so one question is our universe typical? You know, even if we have you know, many universes with some generic behavior, and ours is not one of these generic behavior. And to try to address this problem of predictability, we need some measure, we need some probability measure on the possible universes. And from what we know so far, different measures, and everyone has his own favorite measure, whether it's number of observers or volume or energy or whatever. So different measures give different results, and that's a problem. And basically the whole question of okay, what are the predictions of inflation becomes a question of what is the correct measure, what is the correct probability measure on the multiverse. So if that wasn't bad enough, let's discuss the cosmological constant problem. So we know that the universe is accelerating currently, which the simplest parameterization is to say that we have a cosmological constant. If we relate this cosmological constant to 0-point fluctuations of fields, and from what we know of quantum field theory, then naively the energy density of the cosmological constant should behave like m⁴, where m is the cutoff. Now, okay, as a side remark, this is not exactly true because such a cutoff breaks the scaling symmetry. But okay, still with the standard model, it's definitely 60 orders of magnitude above what we observe. And the problem rises at any energy scale. If we consider the QCD scale, if we consider the Weak scale, the Planck scale, in all of them, as you can see, this is a tens of orders of magnitude difference than what we observe. So this is the so-called cosmological constant problem. And of course, there have been many suggestions on how to address that problem. Symmetries, you know, SUSY was considered something promising, but that doesn't work. Conformal symmetry, trying to modify gravity, Colemannia, which uses wormholes. There are many, many ideas. None of them is compelling, or none of them, I think, gained enough mileage to be accepted by the community and to have, okay, here's an experiment that we can do and verify or falsify that. So if you have a multiverse, you might be very happy because you say, okay, I have a multiverse. Obviously, one possibility is the cosmological constant that we observe. But actually, the multiverse is not enough. The multiverse does generate many universes with many cosmological constants, but they can have any value. And then if I have some flat distribution, for instance, the simplest possible distribution, then obviously I will get the observed CC will be highly unlikely because it will, it will be in a very, very small region of this flat distribution. So on top of having the multiverse, in order to solve the cosmological constant problem, I have to invoke the anthropic argument. The anthropic argument basically is saying that, it has to be that way because otherwise we wouldn't be here to ask the question. This is a very loose way to define it. But if we want to define a more precise way, so we know that observers reside in galaxies, and therefore the cosmological constant has to allow for structure formation. And if you do that, then you get a strong bound on the cosmological constant, which is 10 to the minus 121 m Planck to the fourth term using the non-reduced Planck mass. This was suggested by Weinberg in 86 or 7, which is 10 years before the observations that discovered the cosmological constant. So this is a prediction. If you use this anthropic argument and you use again the flat distribution, then you would think that the most likely value is close to this bound, and it is. I mean, this is written in this is the observation. The observed value is this 10 to the 100 to the minus 119, and here I'm writing the reduced Planck mass, and this is okay. This is within this bound, so this and close to the limit. So this is definitely valid. And this is how people say, okay, this is how the anthropic principle plus the multiverse solves the cosmological constant problem. Now, I think that both ideas are rather hard to swallow. And specifically, I think that the anthropic principle is not really a solution. It's simply a statement that I think the problem is not interesting and I'm working on other problems. Okay, so, and obviously both of them seem very difficult either to falsify. I mean, falsification of the anthropic principle will simply say, okay, here I found some, I don't know, some symmetry or whatever argument that seems rigorous. And then if I can somehow verify with experiments, so maybe that's falsifiable. And can we make meaningful predictions? And what I'm going to advocate here is let's think about statistical physics arguments. And how can that help us? And actually, since I didn't like any of these ideas, neither the multiverse nor the anthropic principle, I thought, okay, maybe I will be able to disprove them. But actually, we found what we got in the end is actually well, not the opposite, but we did find that we can make predictions in the multiverse, but without the anthropic principle, which I think is nice because, yeah. Whenever you find the anthropic principle is always used as a last resort to some problem. So if we can get away from this last resort, that's good. The logic that I'll be using is what Eddington says, that the second law of thermodynamics. This is the supreme law, supreme position of laws of nature. If someone points out to you that your pet theory of the universe is in disagreement with Maxwell equations, then so much the worse for the Maxwell's equation. If it is found to be contradicted by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. So I'll try to use the laws of statistical physics and apply them on the multiverse. So the picture is very simple. So I list here the assumptions of the model, and then I will derive the conclusions, the results. So we assume that we think of each universe as some particle in a multiverse, which is a bath of universes. These universes are semi-classical, so they are larger than Planck size, and the multiverse also, the eternal inflation multiverse picture makes sense semi-classically. We will have a volume for the multiverse, which will be the union of all volumes, because they can be infinities. We will then later for practical purpose, we'll simplify them to be a sum of volumes. The energy should be the union of all energies. And obviously, as we described, we're creating more and more universes. And lots of universes are collapsing because they have if they have a negative cosmological constant, they collapse immediately. So the number of universes is definitely not conserved. So we need a grand canonical potential or grand canonical ensemble to deal with that system. What is the chemical potential? So what do we have? We have that if the inflaton field is below the eternal inflation regime, we don't reproduce universes. We have a single universe. While if it's above it, we produce universes again and again and again. So this should be roughly our chemical potential. It's roughly 10 times n Planck, depending on your model. In the m² phi² model, it's like 10 cubed, but this is ruled out. But the Starobinsky model, which is a good fit, is order 10. The energy density of each universe is approximated by the cosmological constant, and we neglect the other contributions in the meantime. Universes with negative cosmological constant crunch, and therefore will not contribute to the ensemble. And finally, so we're discussing a grand canonical potential and ensemble, so we need a temperature. So I will have to define what is this temperature. And of course, if I want to be in the regime of semi-classical gravity, then this temperature has to be sub-Planckian. So these are the assumptions, and they all give rise at the end of the day to a grand canonical potential of the multiverse. Do people have any comments about the assumptions or reservations?
So you have to. So you should treat these, all the universes are somehow treated as in they are in equilibrium. Is that the idea?
So each separate universe is like a particle. The particle by itself is not in thermal equilibrium, but between the particles, between the universe, the idea is that they will reach some thermal equilibrium.
So okay, and so so there is some. I feel like there is some dynamical input that is already going in the fact that you're ruling out universes without. So the universes are by construction, in some sense, the cosmological constant is going to be positive here, right?
Yeah, zero or positive, yes.
Okay, so
the reason is that negative. Okay, maybe this argument can be refined a bit, but okay, universes with negative cosmological constant will crunch, so they will not contribute. They will not survive long. They will not contribute to the thermalization. That's the argument.
Okay, yeah, I mean, maybe you can go ahead and then I'll ask if I have more questions.
Okay, sure. So yeah, maybe comments that I thought of mentioning about the assumptions is the chemical potential. Actually, we'll see that it's only relevant to say whether it's negligible or not. When we try to compare it to the energy of each universe, and what we get is that it is negligible, which makes sense, right? If we can get new and more universes all the time, it means that it's like photons, right? It doesn't cost us to generate them. The volume, so you can say that maybe this volume of sum of volumes is not a good idea. So you can of course generalize it and say that the multiverse by itself has some volume. That will not modify our results. And we do not say what is each. So we treat each universe as a particle, let's say, but we do not say whether these are these particles have bosonic, fermionic, or other statistics. It can be any type of, certainly these three types of statistics, but all of them give the same conclusion. So how do we define a temperature? So let's say we have a universe. Each universe has some volume, cosmological constant, pressure, and energy. And then this is like a textbook of statistical mechanics. So we have the total, let's say start with some microcanonical ensemble of n universes in volume V. And so then, the total energy of the multiverse is written here. And the total entropy of the multiverse is this formula. Now, if we want to reach equilibrium, let's assume that the universe can change its CC, its cosmological constant, while not changing the volume. For example, by discharging of brains, right? This like a Brown-Teitelbaum mechanism or some other similar mechanism. So, right, so this will induce an entropy change and an energy change. And this is how we define our temperature. So from that, we reach a canonical ensemble with probability density, which is exponentially suppressed. We can then write formally the partition function, and we can repeat the same procedure without fixing n, and by the same variational argument, get a grand canonical ensemble. Okay, so this is our definition of temperature of the multiverse.
So this will be dominated by large volumes, is that correct? Or?
The large volumes will give you the okay. So yeah, here. So obviously.
So I'm a little bit worried whether the fact that if you put in large sizes for the universe, I think it'll automatically dominate that, wouldn't it? So, if the universe is large, somehow the cosmological constant is small, right?
Right.
Compared to the Planck scale.
Yeah. But as you can see, so actually it looks very suspicious because it means that this will be extremely small contribution, right?
No, but I'm saying that if you're using this to compute like I mean, it's so the aim of these ensemble type arguments for cosmological constant is that basically you're trying to find sort of the expectation value of the lambda, right?
Right.
So in that kind of a setting, I'm trying to. It seems to me that if the volumes of the universe are assumed to be large, they will automatically force your lambda to be small, wouldn't it? I mean, it's that
right. But you will see that actually this is not what we get. So okay, you'll see what you'll see that actually small universes contribute quite a lot, and yeah. Okay, so we have the grand potential. And then we can calculate the average pressure. And I remind you that for a cosmological constant, the average pressure is minus the cosmological constant. So the average cosmological constant in the multiverse, we can derive it from this grand potential or grand partition function, whatever you like. And using this chain rule, so I'm really differentiating with respect to the volume of the whole multiverse. And by the chain rule, it allows me to write such a formula, which is a sum over all universes. Now, the chemical potential, as I said, is about 10 M Planck, and this is much, much smaller than the energy of any of the universes. So basically, you can throw that away. And also, I mean, this is only problematic when for fermions, where the chemical potential is positive. For bosons and the Boltzmann particles, this is not a problem at all. But I just want to say that I can neglect the chemical potential, which gives us the general result. So if in the denominator, this second term, this exponential term is small with respect to this unity, then we get a cosmological constant, which is exponentially suppressed without any anthropic reasoning. Okay, and this is the general result. So if my universe is somehow a grand canonical system, I know that the cosmological constant should not be some algebraic average, but it's a weighted average with exponential suppression of each universe. So this is the general statement. And from now on, what I'll try to do, I'll try to quantify this result more and more. Okay, but so I want to make clear this is the general result. And from now on, I'll try to refine it. So questions so far?
So the idea here is that this expected value of lambda would be small because of these exponential suppressions. Is that correct?
Exactly. Right. Yeah.
I see. So.
Yeah.
So I'm the thing that worries me is that if the size of you said that the energy content of the universe is basically controlled by lambda, and you have a large universe, I'm still worried whether the size of the universe being large is if it is a priori present in the problem, then you are the lambda will necessarily be small, right? I mean, because you are working with this in a particle limit.
Yeah, sure. But I will show you in the next slide that I'm allowing actually, very small, Planck size universes, and they still Okay,
Okay.
so yeah, it's not limited to that. Okay, so basically that we got that for a low temperature, or as you said, large universes, the CC is smaller than finite. Now, what can maybe destroy that? Multiplicity. So, right, if we ignore the multiplicity issue, maybe there's a degeneracy here. But I think this is not a very fair criticism because, at least from what we know in statistical physics, most systems don't have exponential multiplicity. So unless someone argues why I should have definitely some exponential multiplicity cannot destroy this result. The other thing, and this is related to your question, so as you see, we treated the cosmological constant and the volumes as independent quantities, as it has to be according to thermodynamics. I mean, the pressure and the volume are two distinct variables. However, now, okay, if I now want to quantify this result, I need to regulate it somehow. So, right, if the energy is infinite, if the volume is infinite, so I want to somehow regulate this result. So, one thing that people tend to do is consider closed universes which have finite volume. Or what I will do, and this is somehow inspired maybe from holography, is to cut out the volume at the ds horizon, at the de Sitter horizon. One very good property that this has is that this is time independent. So, right, I mean, an immediate question is, okay, when are you evaluating the cosmological constant? At what time of the existence of the universe? So the ds horizon is time independent. And this is related to the cosmological constant. So I can substitute this value of this volume inside this formula. Okay, so here is a relation between the de Sitter horizon and the volume and the cosmological constant. But it doesn't mean that they're dependent variable. Exactly like the equation of state of an ideal gas, PV equals NK Boltzmann T, right? So when I derive this equation, it doesn't mean that V and N were dependent variables, right? They were my state variables. So similarly here, I use the state variables of grand canonical ensemble. I later can use this to evaluate what is the size of this average cosmological constant. So if I do that, let me now substitute this volume into our formula, and so to make it easy, I will parameterize lambda as this alpha to the 4th m Planck, and obviously it has to be between 0 and 1. Then we get the following formula. Now notice that all the contributions of this formula are positive definite. Okay, so all of them, it's enough that one of them will be larger than the observed value, and the whole discussion is ruined, right? The whole idea is ruined. So actually notice that the most dominant contribution here are Planck-sized universes, where alpha is 1. If alpha is unity, then this is the largest contribution to this sum. And this gives you a very weak bound on temperature. It basically tells you that temperature has to be sub-Planckian, which we assumed anyway. So we get no new constraint or no further limitation, even when we allow Planck-sized universes. So as you can see, Planck-sized universes actually dominate this sum, not in this formalism, and not very large universes. And even they contribute only a very small part of the sum. Okay. Now, if I want to quantify it further, so let's assume this is some continuous variable. This integral can be done. The exact formula of this integral with some Earth functions is in the paper. The important point is that this gives a prediction for the temperature of the multiverse to be this value, 0.08 m Planck. And obviously, because of this exponential suppression, I can think of many other distributions which are not uniform here, and still the cosmological constant will converge and be small. So this is the continuum analysis. However, obviously, this continuum is just based on some, is not based on anything, basically. I don't have a prescription for the distribution of cosmological constants in the multiverse. So therefore, let's try to do better, and we do that by quantizing the area of the de Sitter horizon. So this idea was put forward in this paper from 2004 by Xiang and Shen. And this is, you know, as similarly to the way that people quantize the area of a black hole to be roughly, you know, some integer times the Planck scale. So let us do the same for the de Sitter horizon. And this again gives me, so this quantizes the cosmological constant. So the cosmological constant now depends on, you know, cannot have any value, but only quantized value. What is it good for? So now it gives me a definite prescription on how to sum the contributions. How? If I go back to my previous formula here, so I'll have, it can have the same NS, the same quantized value many times. So I should sum on many groups or many sets of cosmological constants. But then I can do the standard trick that we do in statistical physics, which is to replace this sum simply by a sum from 0 to infinity. Okay, so now I really have a sum from an ordered sum from 0 to infinity of all possible contributions to the cosmological constant. Obviously, because of the exponential suppression, only the first term dominates. And this is the first term, n equals 0 term. And when we do that, we will get again a prediction for the temperature of the multiverse. So when we evaluate that, simply the lowest order term, we get that the temperature is roughly 10 to the minus 2 m Planck. So what are the consistency checks that we can do? So first of all, one that I already mentioned, right? We wanted sub-Planckian temperature, and to the fact that the cosmological constant is small, and even the largest contribution has to be smaller than the observed value, did not put any additional limitation. It simply said that the temperature is sub-Planckian. The second is that actually, if I look at this 10 to the minus 2, so this is roughly the GATT scale, which is the natural scale of inflation. So this, I think, is another consistency check that we get results that seem natural or reasonable. And finally, actually, if you try to calculate the potential at the eternal inflation regime, what is the value of the energy of the potential? Again, it corresponds to this energy scale. So we have here 3 consistency checks that show that our analysis is reasonable, and we're getting what we should expect to get. So this is all. Okay. So this is basically the results, and then from here we can have a discussion on the implications and what does it mean. So here is what I would like to say about the discussion. So first of all, as I said, the main problem of the multiverse is the loss of predictability. And does it make sense to predict anything within this framework? How do we do predictions if we have no idea what the measure should be? Worse, as I said, for the cosmological constant, this multiverse is not enough, and we need to add anthropic reasoning to explain the smallness of the CC, of the cosmological constant. In our method, what we said is, okay, let's simply say that the multiverse is a thermodynamical system that has to abide by the laws of thermodynamics. It has to equilibrate. From that, we get that the multiverse does make sense in making predictions. It does give us predictions. And the one definite prediction that we did get is that we got a small and positive cosmological constant without anthropic reasoning. Now, if you want to object, you can definitely say that, okay, what have you done? You simply traded the smallness of the cosmological constant for a temperature of the multiverse. This is definitely true. This is exactly what I did. And of course, okay, in principle, I have no idea how to calculate or what is the temperature of this multiverse, but we did get a temperature. This temperature is at the natural scale that we would expect it to be, like a couple of order of magnitudes below the Planck scale. And this is, of course, not a very strong hierarchy problem, basically no hierarchy problem, unlike what we had with the cosmological constant. The true question is, okay, can we think of how to derive this temperature using other considerations? Can we think of an experiment to verify that? So there are some things that I want to say here. Is that one is that, at least to me, this idea seems suggestive. So if the whole multiverse was a single de Sitter space, then that would be its temperature. And if I could plug in this temperature into the cosmological constant, the average of the cosmological constant, I will get exactly this very huge suppression. However, we cannot do that. I cannot, if I want to say that the multiverse is a single de Sitter space, then I invalidate my whole analysis. That's one thing. The other thing is, what about other energy components? Do I have a problem of so I produced an empty universe. So what does that help me? There are many, many ideas of producing empty universes. So actually, this is not exactly true, because we can add pressureless dust or simply dark matter to the analysis, and that will not alter the average of the cosmological constant. So the exponential suppression of such universes will be larger, but it will still give me a small, exponentially small positive cosmological constant. So we're not just creating here empty universes. And the other thing is, okay, this is maybe more of how one can envision that, is that, okay, universes are
that last statement that you made, I think, is roughly related to the fact that if you add matter, you basically make the de Sitter horizon smaller, right?
Sorry, if you add matter?
You make the de Sitter horizon smaller. I think that's essentially tied to the fact that when you add, the pressureless dust statement that you made, I think is probably related to that, I think. So if you have, let's say,
if you dominate by matter, if you are dominated by matter, then
if you add matter to a de Sitter space, its de Sitter horizon comes closer.
Right.
So I think it seems to me that, so that this should, I think, yeah, I mean, I'm just agreeing with you, but so yeah, I mean, I'm just saying that the dust will not, I mean, dust or matter, I would not think that it would anyway create a problem for this argument.
Okay, no, but okay, at least in my opinion, radiation, for instance, may create a problem, because then, can you interpret the varying the grand potential to get the pressure? Can you interpret that as a cosmological, as the minus the cosmological constant? So that's why, but okay, then you can say, okay, I simply want to do an average of the cosmological constant, regardless whether it's related to the pressure or not. But okay, this is why I mentioned that.
So the general, I think the key ingredient in some sense is that there's an exponential suppression where which is linear in lambda, but the thing that multiplies is some power of lambda, some inverse power of lambda, which is smaller than 1. That was the kind of the key technical thing that you needed, I think, right?
Right.
So so that I suspect will not be seriously affected by other forms of matter. So I mean, anyway, that's my speculation. I mean, that's my feeling.
Yeah. Okay, this is the second point. So I think that, okay, if this is correct, then I think this is a good enough in the sense that, okay, the universes don't have to be thermally coupled all the time. So we can think of something like that. There is a phase of that during eternal inflation, that universes with different cosmological constant and volumes equilibrate, mostly if they are produced at the same times, with some finite time slice. And then at some point, like virialization or something, they decouple. And when they decouple, they inflate according to the standard slow scenario, and then reheat, radiation domination, etc., etc. This is some way that we are trying to envision this process. And finally, since I expressed my dislike about the multiverse and the anthropic principle. So actually, the one final thing that I think is interesting is that quantization actually allows us to interpret the system differently. So we don't have to buy the multiverse anymore. We can simply say, okay, I have here a universe with energy, with energy levels. And then I still need thermalization. I still need, right, some bath to say that I have temperature and get the result that I got. But actually, we know that this is much simpler, right? We know that it's enough that you have two simpler systems, two spins, that you trace over one of them, and you get, you get thermal behavior. So tracing, having a system where we trace half of it and getting a thermal behavior, this is easy. For that, we don't need the multiverse. We can think of brain world scenarios, extra dimensions, global or local interacting universes. And so, right, I mean, we know that, Randall-Sundrum models or other models, right, you have two brains. One is our world, the other is used to explain the Higgs mass or whatever. So, we can use such constructions and say, okay, if we trace on one of them, our brain or whatever will see this thermal behavior and will explain the smallness of the cosmological constant. So that's what I have to say, which is obviously with a lot of assumptions and speculations, but I still think it's very interesting, and I'm now ready to take your questions. So thank you. Hello?
Yes, yeah. I mean, if anybody has any questions, please go ahead. I think I asked my questions anyway, and I think, yeah.
Let's see, is there in the chat someone is asking?
Yeah. As I said, this morning time is not when we have our most traffic in our talks.
Okay, that's fine.
Unfortunate. Yeah.
Okay. So
So
thanks
I think
a lot.
I'll just ask one kind of a general question.
Mhm.
So yeah. So So the general right. Yeah, I think so. The basic message is that. So the Boltzmann suppression is what is giving you the hierarchy here at the very the hierarchy that is needed to do this.
Yeah. The exponential, the smallness of the this huge exponential suppression. This is what gives me the small cosmological constant. Sure. Yeah.
Yeah. Okay. Yeah. So I think that's great. I think yeah. Thank you very much.